Hi everyone, welcome back to our channel. I hope you and your family members are doing good because that is the most important thing, and for rest we are here to talk. So we were following our pattern wise DSA sheet. In this we were doing tree topic, and today we'll solve the question from BFS pattern, and the question name is populating next right pointers in each node. So let's read the problem statement. It says we will be given a perfect binary tree where all leaves are on the same level and every parent has two children. The binary tree has the following definition, means instead of only left and right nodes, here there will be one more pointer that is called next, which we have to connect. Initially all next pointers, like for every node, the next pointer are pointing to null values. But after this, we have to connect every node. You can see 2 will get connected to 3 and 3 does not has anything towards its next, means on the same level, so we will connect it to null, which is already connected, so we'll leave it, keep it blank. So let's read the constraint. It says a minimum number of nodes can be 0 also, means base case is required, and the maximum number of nodes can be 2 power 12 minus 1, which is, if you know 2 power 10 is 1024, so 2 power 11 will be 2000 something and 2 power 12 will be 4000 something, correct? So it's around 5 into 10 power 3 only, okay? So it's around 10 power 3. And the values can also be from minus 1000 to plus 1000. So the values, why we read this? Because if we have to do multiplication or addition, then we have to take this very carefully, because the multiplication of a big integer values might become very large that an integer cannot hold, and in that case we have to store it in long variable, long format. But here it is not required. Why? Because we are like we don't have to play with the values, instead we just have to connect the nodes, correct? So minus 1000 to plus 1000 is in the safe zone, and as you can see the definition, it will have value, means every node will have value, will have left child, will have right child which is pointer, and will have next pointer which is initially pointing to null, and we have to connect it. Okay, so this is the tree we will be given, and we have to connect the nodes such that the tree will look like this. Remember, we do not need to return anything, we just have to connect their nodes with the next. So if you see this carefully, like as of now what we have learned the DFS pattern and we have learned the BFS pattern, correct? DFS means depth wise and BFS means level wise. So here from this diagram, what you feel, you should apply DFS logic or you should apply the breadth first search logic. Definitely you can also feel it is something related to level order traversal, correct? So if we have to do the level or traversal, what do you think? For the very first level, we have not connected anything. Remember, let me show you very carefully. Initially, every node next are connected to null. Remember, null, 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 null. Okay. But once we traverse here, as we do not have any node towards its next, so we have not touched it. Means by default, it is connected to null. Now coming to this 2, we have connected to 3. Why? Because after 2 it's there. Similarly for 4 we have connected to 5, for 5 we have connected to 6, and 6 we have connected to 7, but 7 we have not connected because this is the last node. So don't you think in every level except the last nodes, if the index is not last node, why I said index? Because if we will do the level order traversal, level means suppose you did level order, so you will be like 1, 2, 3 in the next level, 4, 5, 6, 7 in the next level. Done. Now we'll start iterating. So index is 0, but this index is also size minus 1. So hence we will not apply logic in this. Now index is 0, size is 2, size minus 1 is 1. So this is not equal. So if the index, again, if the index I is less than size minus 1, then we can say key whatever node we have dot next connect to this child which is 3, but where we have saved this 3. So let's try to understand this with breadth first search approach. So in breadth first search, what we would have done? So first of all we will create a queue data structure, and in queue first we will insert node 1. Done. Now what we'll do, we run the while loop until our queue is not empty, correct? Yes. And now what we will do? Very first we will calculate the size. Size is nothing but q dot size. Done. Now what we did, for that many size, like whatever is the size of the queue, that represents how many number of nodes we have in that level, correct? But we are talking about particular level. So hence we have to run the for loop also, that we already did in our level order traversal. If you have any doubt why are we writing the code like this, again saying we have done already multiple times, so I'll attach the link somewhere here, you can check it out. So we have run the for loop for that many times. Now what we'll do, we'll pop the node. So we will pop the node from queue. So queue dot pull. Now we have popped the node. Now what was our task? We'll pop the node first, and now we'll check ki is this index I is equal to size minus 1. Why size? Because this size is currently referring to the particular level size, which is 1, correct? So as if the index is size minus 1, it means this is the last node in that level, and for that last node we do not need to connect its next to anything, because by default it will be null. Can I say that? So what I'll do, if I is less than, not equal to, sorry, if I is less than size minus 1, in this case it is not, correct? Why? Because I is also 0, yes, and size was 1, 1 minus 1, 0, so it is not less than, it is equal to. So if it is equal to, we will not connect its next to anything. Now what is my task? We are done with this node? Yes, we are done. What were we supposed to do? We were supposed to do like to connect the nodes next to the next node if present, but here it was not present. So now our task is to add their children in the queue, correct? So what we do, what we write, ki if node dot left child exist, then in queue offer node dot left. Similarly, if node dot right child exist, then in queue we will offer node dot right child. Can I say that? Yes. So now as we have popped 1, correct? So 2 will get inserted, and what? 3 will get inserted as their children's. Now next time again size will get calculated because queue is not empty. Now this for loop will run for 2 times because second level contains 2 elements, correct? So first we will pop the element which is 2. Now for 2 what we'll do? We'll check if I, which is index of 2, is less than size minus 1. What is size? 2 minus 1, 1. I is 0. Is 0 less than 1? Yes. So I can say this is the index which is less than the last node, means towards its next, means on the same level there are further more elements present. So our task is to connect this node to the next. But wait, this has been popped and we have stored in node. Now this we want to connect with 3. Where is this 3 sitting? Can I say after popping q dot top element? So if we'll do q dot peak, that is nothing but the next element in that same level, because in q till that size the elements we have are present on the same levels, correct? So what we'll do, node dot next will connect to what? 3. And where is 3 sitting? Q top, which we want to just read. So that's why peak, not pole. We will not pop 3. Pop we will do once again, we'll come here and again we'll check. So 2 we have connected. So what we did, 2 dot next we have connected. So now this has been connected. Now further 2 children and 3 children will add. So first 2 has been popped. So 2 children will get added, which is 4 and 5. Again next time will come, 3 will get popped. Yes, but the index for 3 was, if you remember, index for 3 is 1. Size minus 1, 2 minus 1 is 1. So is it like 1 less than 1? No, it means this is the last node present in that level. So we do not need to connect its next to anyone, because if we will do that, for last node also connect q dot peak. So what will happen? 3 dot next will get connected to 4, because 4 is the what? Like in the queue, it's the top element, which is not from this level. So hence we need to stop. Now what we did, again for 3 also 6 and 7 will get added in the queue, correct? Yes. So 6 and 7 will get added. Now next time we'll come here, queue is empty, no, size is 4. So 4 time it will run. First we'll pop 4. When we popped 4, index was 0, size 4 minus 1, 3. Is 0 less than 3? Yes. So node dot next, which is 4 dot next, connect to q dot peak, and q dot peak is 5. So we'll connect its peak like next to 5. Similarly, next time we'll pop 5, because for 4 there are no children, so we'll not insert anything. Now next time when we'll pop 5, for 5 also index is 1. Size minus 1 is 3. 1 less than 3? Yes. So again 5 next will get connected to q dot peak, which is 6. Next time again we'll pop 6. For 6 we'll check index is 2. Size minus 1 is 3. 2 less than 3? Yes. So no dot next, which is 6 dot next, will connect to q dot peak, which is 7. So this will also get connected. Now again we'll pop 7. When we'll pop 7, index of 7 is 3. 3 less than 3? No. So hence we'll not connect. So by default it will be null. And this is what we were supposed to do. We were not supposed to return anything here. Okay. So if you talk about the time complexity, you all know that for every node you have reached, you have inserted in the queue, and every node you have popped also from the queue, correct? So O of n time complexity, space was also O of n. Why? Because every node you inserted, 1 you inserted, then 1 you popped, 2, 3 you inserted, then 2 you popped, 4, 5 you inserted, then 3 you popped, and 6, 7 you have inserted. So at max you have inserted the last level number of nodes, which is the at max in the worst case, correct? And as it says it is a perfect binary tree, every node will have 2 children. So it means in worst condition it will end up inserting all the nodes present at that level, like last level, and last level contains how many elements? Total n divided by 2. Can I say that? Which is linear only. So hence space and time both are linear. So can we write the code for this in the editor? So here is the code what we have discussed. First we'll check the base case, because the question itself mentions in the constraint part that the node can be 0 also. Or else if it is not 0, we'll start queue, and in queue we'll offer root until it is empty. We'll calculate the size. For that many size we'll run the for loop and pop the node. Now we'll check the index. If it is less than size minus 1, it means it should not be the last element of that level. If it is not, then no dot next, we have to connect with q dot peak, or else we have to insert their left and right children. Once we are outside the while loop, we will return the root, correct? So this was a Java code. Here is the C++ code with a similar approach, and here is the Python code with a similar approach. But this was the breadth first search code. Now what if you have to think for the similar approach but for DFS? Remember, as a beginner level, this is your optimized code also, and more easier also, because whenever we need to play with or something with on levels, then we mostly prefer the breadth first search approach instead of depth first search. But as we are doing both approaches whenever it is possible, so hence we have to do the DFS approach also for the same problem. Okay, so now we'll think about the DFS approach and how DFS approach, how to think for DFS approach in this problem. We all know that for DFS we always starts from root and we go towards either left or right, but in depth. So then we'll go to 2, then we'll go to 4. So when we are at 2, we don't have access to 3. So how can we connect 2 to 3? Think again. Now we are at 1. When we will be at 2? How can we go to 3? One way is if you are thinking ki let's do the level or traversal using DFS. Using DFS, let's do the level or traversal and then insert 1, then 2, then 4, correct? Then you went on 5, so 5 then add. Then you went on 3, then 3 add. Then you went on 6, then 6 add and 7 add. But you are wasting extra space complexity. What I did, using the depth first search approach, I did the level or traversal. Okay, means you stored all the elements in the extra array and now you will run, correct, and connect the nodes to next. But instead of saving the node value, you will save the nodes. This is also possible, but why are you wasting extra space complexity of O of n in this? To store elements also, and because you are applying DFS, so stack, like recursive stack, will also take extra O of n space for every calls, right? So it will be don't you think it will be much messy? So there is one more approach, and how it should come to our mind is, first we are present at root, okay? So when you will move to 2, you cannot go to 3. You can't access it, right? But when I was at 1, I have the access to 2 also and 3 also. Can I say that? So when I am at root, can't I do one thing? If my left child exists, then left child dot next connect to root ka right child. What I did? I said ki if my root is not null, first of all root should not null, and along with that root dot left is also not null, correct? Then what I have to do is ki root dot left dot next connect to root dot right. Can I say that? This will work, don't you think? Yes. Root dot left, connect to right. Now, if you're thinking, what if right does not exist? It's okay. If it exists, it will get connected to 3. If it does not exist, it will get connected to null as of now. Can I say that? Yes. Okay. Now, this will get connected, correct? So now we'll move to 2. When we'll move to 2, 2 is already connected to 3. Listen it very carefully. 2 is already connected to 3. Now again we'll do, does 2 has left child? Yes. So 2's left child, which is 4, get connected to right child. But this is okay. But how to connect this 4 and 5 and 6? Very easy. Very easy. How? If 2's right child 5 exists, then 2's right dot next, which is 5 dot next, connect to 6. And what is 6? 6 is nothing but 2's next, which is 3 dot left. Again, what I said, see what I said, if I'm considering ki we have to connect 2's right child, which is 5, because left child to we can connect like this, 2's left connect to right. Now it's time for right child. How we can connect this to some other parent's left child? This we can do how? Ki when we are connecting this level, for sure we would have connected this level with the help of 1, correct? So now we can reach na. We have to connect 2's right. So 2's right, something like 2's 2 dot right dot next, which is 5, connect to 6. What is 6? Can I say 2 dot next, which is 3 and dot left? That's it. Yes. For root you will not do anything. Now to connect someone's left child with right child, if left child exists, do this. And to connect someone's right child to other parent's left child, right child should exist. And then this code, and that's it. Yes. So if you are following our playlist, and you know how to do DFS and BFS order traversals, and if you can break down these two approaches, then you can definitely write the code on your own. So let's write directly in the editor, and then we'll see the time and space complexity for this. So here is the code. First we'll check the base case, and then we'll call the DFS function, and at the end we will return root, because DFS function is going to connect every children's to its next wherever it is possible. Now we'll check if root is null. Definitely we have to return, because this is the base case, and other is root dot left is null. But why we did this is because the question mentions ki this is a perfect binary tree. Every node will have both children's, or it will be a leaf node. So if any node does not have left child, what does it indicate? It does not have right child also. Like when 2 does not have this. So if you are thinking how to connect 5 to 6, it is not possible, because the question itself mentions that it will have both the children's or nothing. So if 4 is not there, for sure 5 will also be not there. So hence it is not necessary to go on their children's when we already know that it is null. That's it. So hence if any of node is null or left is null, return. Okay. Now what we'll do, ki if left was not null, then only we are at line number 17. So if we are at line number 17, we will connect node dot left next to node dot right. That's what we discussed. And now node dot right next connect to the next parent's left children only when next exists. What I said. See, if you want to connect 7 to someone's next, you don't know na, you can only connect to the other parent's left when your parent has its left next child. Why it is required? Here for 2, when you want to connect 5 children, 5 next to 6, it is very important that 2 should have its next child. Then only you can connect to this. Okay. Why no need to check if it has right child or not? Because again the question what it mentions, if left child is there, for sure right child will also be there. Correct. And now if right child is there, we have to connect right's next, correct, to parents next children's left. So if we want to connect 5's next to 6, it is very important that 2 should have next children, which is 3. Here though it is. Why it is required to check? Suppose here you are, here we have 7. And here by seeing though we can say that 7 does not have any child towards right. But as per the code, how code will understand? So 7 will not get connected to the next children because its parent, which was 3, does not have next. So hence if node dot next is not null, means if node parents next is present, so for sure parents right child dot next needs to be connected with their left child. Done. And now go on left child and right child, because this is a DFS call. So this was your DFS function. We connected every node through the next node with the DFS like this. And here you can connect the level nodes, but not by actually standing on that level, but standing one level ahead, because it is DFS and you can have only one node access. So when we wanted to connect this node to next, so it is not possible, because at a single time a function can hold only one node. So hence it was only possible when we are present one node or one level ahead and then connecting their childrens. It is possible with DFS, but with BFS we saw how we did by storing the elements in the queue, acknowledging that we already have the next childrens present in our queue. Okay, so this was your code. Let's try to run this and let's submit this. Talking about the time complexity, here also we are going on every node by one time, correct? So O of n time, and space wise internal stack is using extra space, which is O of n. So space wise and time wise, both BFS and DFS approach will be same. So this is a Java code. Here is a C++ code with a similar approach, and here is a Python code with a similar approach. So if you understood, we can go in the sheet and mark the next question as done. Hoping you all would have understood and will submit on your own by making your own notes on daily basis, so that you can revise it on a bi-weekly or weekly basis. And if you understood the whole video, make sure to hit the like button and subscribe the channel if not yet subscribed. And you can even recommend this channel to your friends who want to learn DSA with patterns. I have attached the sheet link and my social media links in the description below. Let's meet in another video with some more interesting questions, topics and patterns. Till then, keep learning, take care of yourself and your family.